Those who have joined the class can give their attendance. I repeat, those who have joined the class can give their attendance in the chat box. I will wait for 1 more minute and then I will start the class. Okay, the time is 11:35 a.m. I will not waste further time. Give me a minute so that I can present my screen. Can anyone respond whether my screen is visible or not? My slides?
Yes, sir.
Okay, okay.
Good morning,
So,
sir.
good morning, good morning. Fine. So, before starting today's class, let me give you a brief recap of what we have did in the last class. If you remember, in the last class, we we have solved this heat transfer problem related to weighted residual method. After that, we have started the topic of variational method. I told you that in FEM there are two approaches to solve the problem, to get the approximate solution of a problem. One is your weighted residual technique. One is your weighted residual technique, and the other one is the variational approach. And in variational approach, I also told you that we write the governing differential equation in integral form, and then we try to minimize that integral equation by some methods. That is a variational approach. And in variational approach, there is one method, that is Rayleigh-Ritz method. And in Rayleigh-Ritz method, I also told you that there is a small concept of potential energy approach in FEM. So in the last class, I have told you about this potential energy approach. I have told you that the total potential or potential energy or potential function of any body is given by the summation of internal energy as well as the external energy. And I also told you in the last class that this external energies are all negative energies. These are the energies that is done by the external force on the body. So we are treating it as a negative energy. So the resulting equation of potential becomes pi is equal to U minus W. What is U? U is the strain energy stored in the body. And then we have, I have told you these formula. This is the formula for strain energy, and this is the formula for the external work done by the external force on the body. Again, it has three components, that is the work done due to traction force. Traction force is nothing but the force that is applied on the surface of any structure, for example UDL. And this is the work done due to the body force present in the component. Body force is nothing but the self weight of the object itself. And the last work done is the work done due to point load at at any particular nodal point. This I represents the nodal point at which the point load is acting. Say if on a beam at node point number 2, unit load is acting. Say a load of 50 Newton magnitude is acting. Then this value will be P of 2. I is 2. I means the node where that particular unit load is acting. And this value of I again will become 2. That means you need to find out the deflection at the second nodal point. And also I have told you that if it is a beam problem, what will be the expression for strain energy in integral form? Already you have studied all these things in your strength of material, but here we have to define every equation in terms of integral form. That is variational approach. So for a beam problem, this is the expression for strain energy. For and if UDL is acting, that means if attraction force is acting, this is the expression for work done, and for a point load, this is the expression. I represent the nodal point where the point load is acting, and for a bar problem, this is the expression for strain energy, and for a point load, W is equal to P into U of I. For a spring problem, that same strain energy becomes half into K into delta square. What is delta? Delta is the deflection of the two nodal point. If you are having a spring, that spring is represented by two nodes. Say the first node is node number 1, second node is node number 2, and if the deflection of the second nodal point is greater than that of first one, then the value of this delta will be U2 minus U1, and the point load acting in the spring is again given by that same expression, that is P into UI. I hope in the last class we have discussed till this topic. If anyone can respond.
Yes, sir.
Okay, fine. So in today's class, we will be starting the last topic of this module, that is the Rayleigh-Ritz method. What is Rayleigh-Ritz method? Rayleigh-Ritz method is a variational method. Rayleigh-Ritz method is a variational approach. Rayleigh-Ritz method is a variational approach or a variational method to find out the approximate solution of several boundary value problems, satisfying governing differential equations as well as the boundary condition. Rayleigh-Ritz method uses the concept of potential energy approach. That means in this Rayleigh-Ritz method, I have to convert my governing differential equation into an integral form. And that integral form will be nothing but the total potential energy or potential function of the entire problem. That means the very first step in Rayleigh-Ritz method is formulation of total potential energy of the system or potential function. You can call this phi as potential energy or potential function. So the very first step is formulation of potential function of the problem, and that is nothing but pi is equal to summation of internal energy plus summation of external energies. So external energies are all negative in nature. So the resulting expression for the total potential becomes pi is equal to U minus W. Just now I have told you that U will vary from problem to problem. If it is a bar problem, you have to use that particular expression to solve the problem. If it is a beam problem, you have to use that particular expression of U to solve the problem. So is the first step clear? The very first step is formulation of potential function of the problem in terms of strain energy stored in the problem as well as the external work done by the external forces in the given problem. Is it clear? The first step?
Yes, sir. Clear.
Okay. What is the second step? If you remember the weighted residual method, what we were doing in the second step? In the second step, we were assuming some shape functions. Those shape functions can be trigonometric functions as well as polynomial functions. Here also, in the second step, after the formulation of total potential of the problem, we need to assume a suitable displacement field. Displacement field is nothing but the shape function of the problem or the trial function of the problem. Here we will not call it as trial function, we will call it as a displacement field because we have used already trial function for the Galerkin method, for the weighted residual method. So let us call that trial function in Rayleigh-Ritz method as a suitable displacement field. You also know that this displacement field can be a polynomial function, it can be a trigonometric function. Again, you can choose higher order polynomial also, you can choose a lower order polynomial function also. If you choose the higher order polynomial function, your result will be more accurate. If you choose the lower order polynomial function, your results will be less accurate. But keep one thing in mind while selecting or while choosing these displacement functions: the displacement field or the displacement function should satisfy both the essential boundary condition of the problem. I have already told you in the previous lectures what is essential boundary condition, as well as the internal compatibility of the problem. Internal compatibility means there should be no kinks, voids, etc. within the structure. That means there should be no discontinuities present in the structure. Means this displacement function should satisfy firstly the essential boundary conditions of the problem, and secondly, while applying these displacement fields, you should keep in mind that the problem or the domain over which you are applying these displacement fields, that domain should not contain any kind of crack, any kind of voids, or any kind of kinks. So we can choose a linear polynomial function, that is a naught plus a1x. We can choose a quadratic polynomial function, that is a naught plus a1x plus a2x square. We can choose higher order polynomial functions also, that is a naught plus a1x plus a2x cube plus dash 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 dash. Similarly, if beam is given to you and if the beam is bending, then I know that the bending curve follows some sinusoidal curve, follows some cosine curves. In that case, these trigonometric functions will not be suitable displacement function to solve the problem. So in those cases, we have to take the trigonometric functions. That is, u is equal to a1 sine pi x by l plus a2 sine 3 pi x by l plus dash 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 and so on. So this is the second step in Rayleigh-Ritz method. That is assumption of suitable displacement field, keeping in mind that it should satisfy essential boundary conditions as well as there should not be any kind of crack or damage or voids present in the structure. Is it clear? The second step. Any doubt in this step? Hello.
Yes, sir. Yes, sir.
Is there any doubt in the second step?
No, sir. No, sir.
Okay. Third step. Now, if you remember the weighted residual method, in weighted residual methods, we were having four methods. That is, the first one was your least square method. Second one was point collocation method. Third method was Galerkin method. So in those cases, what we were doing, we were finding out the domain residual of the problem. If you remember, in the weighted residual methods, we were finding the domain residual of the problem, and then we were trying to minimize that domain residual by all these techniques. If you use Galerkin method, then how you can minimize that domain residual? You have to take the product of weighted function, which is your given trial function, and the residue, and then you have to integrate it over the entire domain equal to 0. But in this method, we will not compute the residual of the problem. What we will compute in third step, we will substitute the value of assumed displacement field after applying the essential boundary condition in the total potential energy. Normally what we do, we calculate the residual, but here already we have formulated the governing differential equation of the problem in terms of potential energy approach, which is an integral equation. So I will not use the residue. What I will do, I will use the assumed displacement field. Then I will try to find out some unknown values, unknown coefficients by the use of essential boundary conditions. Once that unknown coefficient values I have found out, then the resulting or the new displacement field after substituting the values of unknown coefficient, you will substitute that value of u in your given potential function. That is your step number 3. That is formulation of new potential function of the problem by substituting the assumed displacement field in step number 2. From step number 2, this particular assumed displacement field, after applying the essential boundary conditions, you have to substitute it in step number 1. Then what will happen? Then the modified form of the potential function of the problem will be generated, which will be in terms of your assumed displacement field. This is the third step in Rayleigh-Ritz method. Is it clear?
Yes, sir.
Okay. Next step. If you remember the weighted residual method, after the calculation of domain residual by different techniques, we were minimizing that residual. But in this method, in Rayleigh-Ritz method, we have to minimize the modified potential function of the problem. Objective of Rayleigh-Ritz method is to minimize the modified potential function of the problem. How you can minimize it? For that, you have to take the partial derivative of the modified potential function with respect to the unknown constant present in the assumed displacement field. Say if you have taken the second order approximation, that is u is equal to a naught plus a1x plus a2x square. You are having essential boundary conditions. Fine. With the help of essential boundary conditions, say you have found out the value of a naught. Then the new assumed displacement field will be u is equal to that particular value of a naught plus a1x plus a2x square. Then you put this value of u in equation number, in the first step you will get the modified form of your potential function. Now in that modified form, if you see that there are two unknown present, that is unknown constant a1 and unknown constant a2. So in the fourth step, you need to minimize your entire potential function means you need to partially differentiate your modified potential function with those unknown coefficient. So I represent 1 comma 2 comma dash 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 comma n. If in a problem there are two unknown coefficient, then the value of I will be 1 and 2. That means if the unknown coefficient is a1 and a2, two times you have to partial differentiate it. That means del pi by del a1 equal to 0 will give you one equation. Second time del pi by del a2 equal to 0, this will give you two, the second equation. You will be having two equations and two unknowns. With those two unknowns you can get the value of a1 and a2. This is step number 4. Is it clear? Step number 4. Any doubt in step number 4? Hello. Please respond whether step number 4 is clear or not.
जी सर जी सर.
Okay, fine. Next is step number 5. So once you get the values of unknown coefficients, that is a1 and a2, by step number 4, that is by minimizing the potential function, then what you will do is you will substitute that unknown coefficient a1 and a2 in the given assumed or in the assumed displacement field. You will substitute the value of a1, you will substitute the value of a2, a0 already you have calculated by the essential boundary condition. Then that value of u will be your approximate solution of the problem by Rayleigh rates method. This is the last step of this method. Is it clear? Step number 5. Any doubt in step number 5? Please respond whether step number 5 is clear or not.
Yes, sir. Yes, sir.
Okay. So this
और फिर
is
से
the, sorry, hello,
एक बार फिर से समझा दीजिए.
last step. Okay, in last step what we will do is, in the fourth step you have minimized your entire potential function by taking the partial derivative of potential function with respect to unknown constant present in the assumed displacement field. So since you have found out the value of a naught by the essential boundary condition, two unknowns are left, a1 and a2. So first time you will partial differentiate your potential function by a1, del pi by del a1 equal to 0. You will get one equation in terms of a1 and a2. Similarly, second time, since there are two unknowns, second unknown is a2. So second time what you will do, you will partial differentiate your potential function by a2, del pi by del a2 equal to 0. Again you will get one equation. So you are having two equations, two unknowns, a1 and a2. You will solve those two equations, you will get the values of a1 and a2. After that, what you will do in fifth step? In fifth step, you will substitute the values of a1 A2 in the assumed displacement field which you have assumed to solve the given problem. Then you will substitute the values of A1 and A2 in the given assumed displacement field. Then that assumed displacement field will be your approximate solution of the problem. This is the last step of Rayleigh rates method. Is it clear?
Yes, sir.
Okay. Now, why this method is known as Rayleigh-Ritz method? Rayleigh and Ritz were the two scientists. Fine. See, this method was first formulated by Rayleigh in 1877, and later on it was refined and generalized by Ritz in 1908. Rayleigh worked with just one term approximation, that is linear approximation. Initially, when Rayleigh has introduced this method, with that method we can take only linear approximated displacement function of the form u is equal to a naught plus a1x. Later on, Ritz modified this method and then he told that no, we can take multiple degree or multiple order of polynomial approximations as well as multiple trigonometric equations we can use. So that's why this method is known as your Rayleigh-Ritz method. They both are different scientists on the basis or because of they have discovered this method, and so on the basis of those scientists' name, this method has been written. So Rayleigh has what he did, he extended this technique to an n-term approximation. That means a naught plus a1x plus a2x cube plus dash 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 dash. How much high order you want, you can take that approximation. Same goes for this trigonometric part also. This method is nothing but a variational approach in which the entire governing differential equation is converted into integral form by the use of potential energy approach. This is the main concept of this method. That means in this method, the entire governing differential equation have to convert into integral equation by potential energy approach, and then the process you have to start from step number 2 and you have to end till this step number 5. So this is a generalized process of Rayleigh-Ritz method. Is it clear? If it is clear, then we will solve one problem today. Is the method clear?
Sir.
Okay. So let us solve a problem by this method. Then everything will be clear to you. Let us read the problem. The problem is a bar clamped at one end and left free at the other end is subjected to a uniform axial load Q naught as shown in the figure. Find the displacement of the bar as a function of x by Rayleigh-Ritz method. What is given to you? Bar is given to you, and this is nothing but a cantilever bar. Domain of the bar varies from x equal to 0 to x equal to L. On this bar, a uniform axial load is acting, that is Q naught, which is shown in the diagram. What you need to find out? You need to find out the displacement of the bar. Let us assume that the displacement of this bar, that means the bar will displace due to this axial load Q naught. Fine, let this displacement is nothing but U, which is a function of x. That is, we need to find it out. Due to this axial load Q naught, how each and every node or how each and every element is displacing by Rayleigh-Ritz method. Is the problem clear?
Ah, sir.
Fine.
Yes,
So
sir. Yes.
what is the very first step? How we can start this problem? See, so far whatever problem we have solved, in each and every problem I have given you the governing differential equation as well as essential and natural boundary conditions. But in this problem, neither I have given you essential boundary condition, nor I have given you natural boundary condition, and neither I have given you governing differential equation. Now you have to assume, so it will be a little bit tricky problem. I haven't given you anything. Now you have to assume. How you will assume? The governing differential equation of the problem. If you remember my 3 4 lecture, my 3 4 lectures back, if you remember, I have given you one. I have given you one table, that is this particular table. Yes, this particular table. If a load is acting on any bar, what will be the governing differential equation? If a moment is acting on a bar, what will be the governing differential equation? If a shear force is acting, what will be the governing differential equation? So you have to apply then these governing differential equations in order to solve such kind of problems where the governing differential equation is not given to you. Clear? And you have to also identify the essential and natural boundary condition of the problem. So can you tell me the natural and essential boundary condition for this problem by looking at the diagram? What can be the essential and natural boundary conditions for this problem by looking at the diagram? You can see that at the fixed end, displacement will be zero. That means
V is equals to 0
that
when
means
x is
you can
equals to
write the
0.
essential boundary condition. Essential means what? In this problem, my essential thing is the displacement. So displacement u will
Ux
be
is equals
zero
to 0.
when x is equal to 0. This is the essential boundary condition of the problem at this particular point. Is it clear?
Yes, sir.
Now I have
Yes, sir.
to
Clear.
find out the natural boundary condition. Though I not require natural boundary conditions to in Rayleigh-Ritz method, but still let us find it out. What is that natural boundary condition? Can you tell me? By looking at the problem, natural boundary condition means the slope, that is du over dx. So can you tell me by looking at the problem what is the natural boundary condition? What will be the value of natural boundary condition? That is du over dx at x equal to L will be equal to 0. Yes or no?
हाँ sir, हाँ sir.
Due to application of load Q naught, there will be no slope at the end point x equal to L. So I can write du over dx at x equal to L is equal to 0. So I can ask this question for weighted residual method also without giving you the governing differential equation and essential and natural boundary conditions. So by looking at the problem, you have to first define the governing differential equation and then the essential and natural boundary conditions. Fine. So these are the two essential and natural boundary conditions for this problem. Now what is very first step in this Rayleigh-Ritz method? Very first step is formulation of potential function for the problem. I know that potential for this problem will be given by pi is equal to U, that is internal energy, plus external energy. Since external energies are all negative in nature, so the resulting equation becomes pi is equal to internal energy, that is nothing but the strain energy stored in the given problem, minus external work done on the problem. This is your equation number 1, where U is what? U is your strain energy stored in the bar. I have told you in the last lecture that for a beam problem, what will be the expression for strain energy, and for a bar problem, what will be the expression of strain energy. Now you tell me that which equation of strain energy I will use to solve this problem. This particular expression, that is this first expression, or this second expression. See the problem? This is the problem.
So second one, I think.
Why second one? Why not first one? Because
बीइंग का प्रॉब्लम है
if
कंटिन्यू
you use first one is applicable for a beam problem. That means if this beam is bending like this, if this beam is bending like this, then I can use that first expression of strain energy. But here bending is not happening. In linear direction, displacement is happening. Fine. So I cannot use that first expression. I have to use the second expression of strain energy. That is U is equal to half E into A. E is the modulus of elasticity of the material of the bar. A is cross-sectional area of the bar. Integral of du over dx, that is slope square, into d of x. So this is the strain energy. U is equal to half E into A. Now I have to integrate it. If you see in the given question, domain varies from x equal to 0 to x equal to L. So the lower limit is 0 and the upper limit is L. U equal to half EA integral of du over dx whole square into dx. Equation number 2. Is it clear?
सर क्लियर है
Okay. Since next step is what? Now I have to find out the value of W, which is the external work done on the body. And if you remember in the last lecture, when I was telling you about the potential energy approach, W is having three components. First component is work done due to traction force. Second component is work done due to body force. Third component is work done due to point load. So now see the diagram and tell me which component will I take. Will I take the traction force component, or will I take the body force component, or I will take the point load component? See the diagram and tell me. Which component will I take for finding out the external work done on the body? बोलो कौन सा वाला यूज करोगे? कौन सा इक्वेशन यूज करोगे, फर्स्ट वन, सेकेंड वन और थर्ड वन? If you see in this entire problem, axial load Q naught is applied on the surface of the problem, and this Q naught is nothing but a UDL. It is present, it is applied on the entire bar. That means this Q naught is what? This Q naught is nothing but a UDL. If this Q naught is UDL, I have to take the traction component. I have to take the traction component of the force, because this traction component, traction force is what? This is the surface force acting on the body, which is nothing but UDL. So here my expression will become W is equal to minus integral x equal to 0 to x equal to L into U. Since I am talking about only the displacement along x direction, so I will take ux, or simply u, into this traction force will become q naught into dx. Is it clear? So your work done will be W equal to minus x equal to 0 to x equal to L integral of q naught into u dx. Equation number 3. There is no body force present in this question. Nowhere it has been told to you that the self weight of this bar is something, and nowhere a point load is acting. So I have to ignore those two work done, and only I will take the work done due to traction force, that is Q naught, and that is given by W equal to minus integral x equal to 0 to x equal to L Q naught into U dx. Equation number 3. Is it clear? Equation number 3. Any doubt?
हाँ सर हाँ.
ओके, बाकी लोगों को क्लियर है? इफ यू कैन रिस्पॉन्ड, अदर पीपल प्लीज रिस्पॉन्ड वेदर इट इज क्लियर और नॉट.
Yes, sir.
ओके, so since we have calculated, we have found out the expression of u as well as we have found out the expression of w, we can substitute the value of u and w from 2 and 3 in equation 1. Then the resulting potential function in integral form becomes pi is equal to half times of EA integral x equal to 0 to x equal to L du over dx whole square dx minus integral 0 to L q naught into u dx. Equation number 4. And this is the potential of the problem. Clear है? Equation number 4.
हाँ सर.
Yes, sir. Yes, sir.
Okay, fine. Next what we need to do now, in the next step we have to assume a shape function or a displacement field of the problem to get the approximate solution. So tell me, which displacement field function will I choose? Will I choose the trigonometric displacement field function, or will I choose the polynomial field function? See the diagram and decide which field function you will choose. Displacement field function, sorry, the polynomial field function or the trigonometric field function.
Polynomial.
Polynomial, because here due to application of this traction force, fine, there will be no bending of this bar, so no need to go for trigonometric
Trigonometry.
function, and that too this bar will be displaced in one direction, fine, that is the x direction. So let us choose polynomial function for that, and that too let us choose higher order polynomial. You can choose linear polynomial function also, but your result will be less accurate. So let us choose second order polynomial function, that the assumed displacement field of this problem is u is equal to a naught plus a1x plus a2x square. So u which is a function of x which is near about equal to a naught plus a1x plus a2x square. Equation number 5. Is it clear? Any doubt?
No, no, sir.
Okay. Next
No,
is
sir.
what? Next, see here now if you see in the displacement field variable there are three unknown coefficient a naught, a1 and a2. With the help of essential boundary condition, let us find out any one of this unknown coefficient. Remember, we cannot use natural boundary condition. There is you cannot use the natural boundary condition in Rayleigh-Ritz method. This condition you can only use in weighted residual method. Fine. So let us use the essential boundary condition of the problem, that is displacement field will be 0 when x is equal to 0. So in equation number 5, let us put value of x 0. Then u will also be 0. So u is 0 which is equal to a naught plus a1 into x 0. a1 into 0 is 0 plus a2 into x is 0. a2 into 0 square is 0. So I get value of a naught is equal to 0. Now this value of a naught I will substitute in equation number 5. Then the modified displacement field of the problem becomes u of x which is near about equal to a1x plus a2x square. Now you can see that the assumed displacement field is having two unknown coefficient. You have to now what you can do, you have to put this displacement field in the assumed or in the modified potential energy or the potential function of the problem. If you see in this potential function, here you have to place the value of u, that is a1 x plus a2x square, and here you have to put the differentiable value of u. That means you have to differentiate this u one time, then that differentiation value, that is du over dx, if you differentiate it with respect to x, it will be ddx of a1 into x is a1 because ddx of x is constant plus a2 into ddx of x square is 2x. So the differentiation of u over x, that is du over dx, becomes a1 plus 2a2x, which is equation number 7. So this is the modified potential of the problem. In this modified potential form, replace du by dx by a1 plus 2a2x and replace u by a1x plus a2x square. Then we have to then you will get one expression of pi. That expression of pi you have to minimize it, and you see in this expression there are two unknown coefficient a1 and a2. So first time you will minimize that pi, you will take the partial differentiation of pi with respect to a1, then you will equate it to 0, that is del pi by del a1 equal to 0. Second time you will partially differentiate the potential function phi with respect to a2, that is del pi by del a2 equal to 0. With these two equations, you will get two equations in terms of a1 and a2. You find out the values of a1 and a2, then substitute the values of a1 and a2 in equation number 6, which is my assumed displacement field. You will get the approximate solution of this problem by Rayleigh-Ritz method. Since the time is not there, so I will discuss the remaining part of the problem in tomorrow's class. Till now, everything is clear till equation number 7. Any doubts till
No,
equation
sir.
number
Sir, it
7?
will only give me the approximate solution.
Yes, all these methods, Rayleigh-Ritz method, weighted residual methods, They don't give the exact solution. They give the approximate solution near to your exact solution value. So till equation number 7, is everything clear? Any doubt?
Yes, sir, clear.
No, sir.
Okay, fine. So with this, I am ending the class over here itself. If anyone is still left to give his or her attendance, you can give, and then you can leave the meeting. Thank you.
Thank you, sir.
Okay,
Thank
okay.
you.